Okay, gonna do a little quick review of the stellar properties unit, which kind of gets into different types of stars other than our sun. The inverse square law of light works much like the inverse square law of gravity, except for obviously it deals with light instead of gravity. But every time you increase a distance, the area of light that is, or the area that the light is covered by is squared. So it covers 4 times as much area at 2 times the distance, 9 times the area at 3 times the distance. So the basic gist of the inverse square law of light is the further away something is, the dimmer it looks. Um, we've given it a unit. It's called the lume. We denoted that, or designated that the sun is 1 lume. It's essentially how much energy something produces per square meter. You have 2 different types of magnitude: apparent and absolute magnitude. Apparent magnitude is how bright a star or a stellar object appears from Earth. Hipparchus was the first one to do this in the 2nd century. He made a star catalog over 500 stars, and he numbered them as to what he thought was the brightest and dimmest. So he went on a scale of 1 to 6. We later included other objects, including our sun and the moon, which he didn't consider stellar objects worthy enough of being given a magnitude, and they had to go negative because of that, because they're brighter than what he classified as number 1. So as a result, we have apparent magnitude with numbers that are negative numbers that are really bright objects, and super large positive numbers are really dim objects. Um, Absolute magnitude is the idea that we move every single star to 10 parsecs away to put everything on a even playing ground, or playing field, so that we can actually compare stars side by side and taking distance out of the equation. And a parsec is 3.3 light years. So 10 of those is 33 light years. So if we could fictitiously move them to that distance away and kind of put them next to each other, that's what it would give us. Absolute magnitude is equivalent to luminosity on the HR diagram, and this scale shows it that both y-axes of the HR diagram are listed here. Luminosity on the left with the sun being at 1, and then the sun being a +5 absolute magnitude. Again, when you compare it to other stars, it's not that bright. Star color and temperature. We reviewed this in the light unit, how we use this information. These are called black body curves, and we can tell a star's color and therefore its size typically, but definitely its light output, by what color it is and where it peaks in this curve. Stars are different colors. Rigel's blue, Betelgeuse red, Orion. This star, it's actually not a star, it's a nebula, is a bright white because it's a lot of hot objects. So blackbody curves really use only 2 filters. We call this the BV filter. It's oftentimes referred to as the BV index, color index. It is a subfield of astronomy known as photometry, which is down here. But we take 2 points by using a filter on a telescope. The B filter rejects all radiation except for violet and blue, the 380 to 480 nanometers. You don't need to know that number, but just the blue. And the V filter stands for visual, but it rejects all radiation but green and yellow. So it's you get a data point for the yellow, how much yellow light something emits, and a data point for how much blue light something emits, and you track the trajectory of that. If it's less yellow, more blue, the trajectory is up, and it's going to be a hotter star. Inversely, if there's more yellow and less blue, it's going to be a colder star or colder stellar object. Spectral classification. It's basically a way to put stars in classes based on surface temperatures, photospheric temperatures. So our sun, for instance, is about 5,800 K, so we're a G star. The larger stars are the O stars. These are blue, super blue stars, and super blue giants. And M is red dwarfs. So these are the coldest surface temperature stars. Acronym, or not acronym, is it acronym? I don't remember. Mnemonic. Is "Oh, be a fine girl or guy and kiss me." So, "Oh, be a fine girl and kiss me." O being the largest. So there's really large stars in the universe. When you compare it to like our star, for instance, our star is a fairly small star. It is a dwarf. It is a yellow dwarf. So this scale or this slide just kind of shows different sizes of some of the stars. Here you see Antares is 500 radii beyond Mars's orbit. Betelgeuse is fairly close, so we're actually able to measure it a little bit easier because here's the size of Earth's orbit. It's about 500 light years. So giants. Giants are stars that have radii between 10 and 100 times that of the sun. Most of them are red. Not all of them. They can be blue. Supergiants are stars that are about 1,000 solar radii. It's kind of an iffy range in between 100 to 1,000. It's typically referred to as supergiant. So that's the symbol for solar radii. Remember, the circle with the dot in the middle means the sun or solar, and then the R is the radii. Dwarfs are any star that's the same size as the sun or smaller. Most of them are red in color. They're not quite bearded. They do not have to burn a lot of fuel to maintain hydrostatic equilibrium. If you remember what that is, that pressure out and gravity in. Because they don't have as much gravity, they don't have to burn as much fuel, so they last a lot longer. And they're therefore burning at cooler temperatures, which makes them red. So white dwarfs are the cores of average-sized stars. They are classified as a dwarf just because of stellar mass-wise. Hertzsprung-Russell diagram, critical for stellar evolution. It's got 4 parameters. If you look up here, you have spectral class, and then you have temperature down here. Well, these 2 variables are related, so it's easy to put them on each side here. And luminosity and absolute magnitude, as we spoke about earlier, are also related. So this is what's considered a quad-axis graph, and it's developed by Danish astronomer Hertzsprung and American astronomer Russell independently. Kind of put the 2 discoveries together to make one big thing. The main sequence is the band of stars right here that kind of goes diagonally, kind of in a twisted way. You have in the upper left, you have blue giants, which are big and luminous and hot. Down here, you have red dwarfs, which are cool and not as bright because they're small. Can't remember what else I was going to say about that. Oh, all stars live about 90% of their life on the main sequence. So, well, there it is. So they fall onto the main sequence after reaching hydrostatic equilibrium. That's the term. So white dwarf and red giant regions. These types of stars don't sit along the main sequence due to their weird properties. So red giants are large and cold because the photosphere is very far from the core. So as a result of that, they're still luminous, but they're cold. So they're all the way in the upper right-hand corner. White dwarfs, inversely, I'll go back to this. White dwarfs, inversely, are going to hang out down here because they're really small, but they're hot, but they're not very luminous. So that's a critical point. A stellar luminosity class. There used to be a 1 through 5 Roman numeral system. They split number 1 into two subtypes. 1A are the bright supergiants, 1B are the supergiants, all the way down to 5, which is the main sequence stars, which that's what the Sun is. The Sun is a 5 stellar luminosity class. This is typically where the luminosity classes land. The stars are somewhere in this region on an HR diagram. 5 is obviously the main sequence. And these 1A, this bright supergiants, are going to be up here for a little bit of time. Then they're going to kind of evolve over this way, which we'll get into in the next unit. So the Sun is a G25 star. And white dwarfs are not luminous enough to be classified. Most stars are in binary systems. You have, I would say, the overwhelming majority of stars are in at least a 2 system and possibly a 3 system. There have been 4 star systems discovered. That's not as common. So we can measure the mass of these things by looking at where the center of mass between the 2 objects are. Helps us get a little clue about how big some of the stars are. Visual binaries are rare because they have to be really close for us to be able to see them. Because typically when you see something like this a long ways away, it just looks like one point of light. So we've only seen a few of those. Spectroscopic binary is the more common way to see them. When we see a star and we look at the spectrum where it should be, and then we see it red shifting, and then we see it blue shifting, that means that the star is not moving away from us and back towards us again. That means that the star is rotating around a common center of mass. So in this sense, the star will be redshifting because what we see is the light from the bigger star. And as it's redshifting away, we see the single point of light as a redshift. Inversely, when it's coming this way to the left, towards the big floating eyeball, this star again is the brighter star, so we see this one blue shifting towards us. There's a little bit of, it's basically exactly what I just said, so feel free to pause it and read it. The eclipse in binary. This also is the easier way to actually than spectroscopic to detect a binary star. When we see both stars sitting side by side, the light intensity is way high. Here it dips because the red star is much less luminous than the yellow star, so as a result we see a drop in intensity of light. Even though it's still a star, it's blocking a lot more light that the yellow star is putting out. 3, we see it return back to position 1. 4, it dips again, but because the red star moves behind it. So in this case, it's not as bright as these two together, but it's not as dim as this situation over here. So the cycle repeats. So when we notice a light dipping like this in a regular pattern, we know that a star is being eclipsed by another star. This is a graph of stellar mass distribution, which is essentially if you took all the stars in the universe, of course theoretically, and you put them into these different classes, most of them, about 96% of all stars, if you include these little kind of brown-red dwarfs all the way through the yellow dwarfs, would account for about 96% of the stars. The other 4% is this smidgen here with the white and the blue. So most stars are dwarfs. Big stars are rare. You have interstellar matter. This kind of gets into how stars are born. Ingredients of star birth is gas and dust. It's a very low density, but of course over time with gravity will start to make things happen. This is the Orion Nebula. Even though the cloud is cold, right, it still has some atomic movement. So it's averages about 2 to 10 Kelvin. Of course, absolute zero is just a couple degrees away from that, so it's ridiculously cold, obviously, but it still has some kinetic movement, which means that it's emitting light, so especially in the infrared. So as gravity slowly starts to contract the cloud, the KE of the nebula increases because particles are hitting each other and it gets hotter and hotter and hotter. So beautiful picture of the Horsehead. Beautiful picture of the Eagle Nebula. One of the most famous ones, also known as the Pillars of Creation. They're really large. I didn't say that. Alright, so how does that get to a star? Collapsing cloud fragments. Well, this thing is a nebula, right? Just like we just looked at, interstellar matter. Something will cause this to start breaking into smaller segments. Obviously, it's gravity, but typically there's something else that is a catalyst for it. These bigger ones will break into these little smaller ones right here, and the smaller ones will eventually start to become solar systems. Larger the cloud, larger the star, that should make sense. And as the cloud continues to collapse on itself, it gets hotter and hotter and hotter because there's more kinetic movement, right? More atoms are hitting each other. That increases temperature. So the timeline is kind of insignificant. Tens of thousands of years. No one really knows about how long this takes, but fragmentation starts to stop and more definitive product starts to result, right? Which will eventually become a star. When the density is high enough that it becomes opaque, the protostar is about 10,000 K in the core, which is very hot. It's hotter than the surface of our sun, but it's not hot enough to do fusion, so it's not a star yet. So because of that, we call it a protostar. Sometime later, I said 100,000 years. I didn't just say that. The book said that. Stars reached about 1,000,000 K. It's about the size of Mercury's orbit. It's much larger. So it gets all its heat from GPE to kinetic. It's not hot enough to fuse hydrogen yet, so it's still not a star. But it's starting to clear out a path here. It's more luminous than the sun because it's so large, right? It's way bigger than the sun. So something that's that hot, that's that big, will still look very bright. So as it contracts, it gets less luminous because it gets hotter. And as it goes down in the HR diagram, it'll start kicking over to the left because it's getting hotter if you look at the scales. So during this stage, the surface exhibits this extreme solar wind, and we refer to the star at this point as the T-Tauri star. This is kind of just a diagram, right? This thing's way huge nebula. Then it breaks into a fragment, and then you have the star starting to form with a disk around it, which will eventually become planets, of course. So when the star reaches stage 6 here, where again you don't need to know those numbers, that's not important, it ignites nuclear fusion. So you have 4 protostar, 5 it starts getting hotter, and I know it's getting hotter because it's going left. I also know it's getting smaller because the solar radii has gotten less, and it's also become way less luminous. At position 6, fusion starts. It takes about 10 million years. It has to reach 10 million K for that to happen. When that happens, it swells up a little bit, gets hotter, gets a little more luminous, but then eventually it'll settle back down on the main sequence. When it settles down on the main sequence is when it's reached hydrostatic equilibrium. The bump between 6 and 7 is because of trying to reach that balance. Bigger stars, smaller stars, they all do the same thing. They just start at different places and fall on at different rates. Bigger stars will fall onto the main sequence at faster rates, smaller stars inverse to that. .08 masses, solar masses, are needed for nuclear fusion. Anything less than that becomes what we call a brown dwarf. So anything above that limit will become a star. So how do they start? Well, nebulas can have to start with or a star has to start with a shock wave within a nebula. Caused by what? Well, that's kind of a question mark. We have some things that we think cause it, but what exactly, caused some of the early stars, that's kind of up for question, right? Could it be possibly a shock wave from the Big Bang? Anyway, These stars up here start to accrete matter. They start fusion. They're probably really large stars because there's a lot of matter at this point. As they reach the T-Tauri stage and start blowing out their solar winds and clearing out their neighborhoods, this causes shock waves, or basically the nebular gas to compress in other regions. Well, this will start a whole new generation of stars to start forming because the gas will start clumping together, gets denser and denser and denser and hotter. Other four different ways they could happen if it's not a ridiculously dense nebula. Need that pressure. We need that shock wave pressure. And one way is the gentle puffing off of the outer layers of a star, a medium-sized star like our sun with a planetary nebula. You have supernova explosions. That's a very typical catalyst for a new star birth. It creates a tremendous pressure out. Spiral arms of a galaxy impacting a nebula. These are things I showed in class as far as pictures and the spiral arms of them impacting a nebula randomly through space, which does occur. And also when two galaxies collide. It could be two. Doesn't matter the size of the galaxy. It's just what you're going to have is opposition rays. Basically, stellar friction, which is kind of bizarre to think. But anyway, it's collision of gases within space because of two things that ran into each other. So, anyway, hopefully you found the video helpful, and study up.